Uranium, thorium, helium applications to Earth system science by Sarah Speeches. This is the final presentation for ESSI 8000. So the research questions and motivations. So while the methodology that I present in this work is primarily geochemistry focused, there's significant room for creative applications of the uranium, thorium, helium system to more interdisciplinary topics. So by refinement of this methodology and the discovery of applications to new mineral phases, this system with corresponding in-depth processing of the resulting data will allow for unconventional questions relating to the interaction of Earth's spheres to be asked and answered. And so while the extensive exploration of new mineral phases that may be useful is really out of the scope of this work, as this is a topic I'm considering pursuing a postdoc in, this work has served as basically a review of the methodology and the state of the research utilizing the uranium, thorium, helium dating method. So an introduction, what is this? This is a radiometric chronometer. Basically, you measure several isotopes that are present in certain mineral phases. So this is based on the radioactive decay of uranium, thorium, and its daughter product, helium. And so essentially, we know these systems, we know them very well. We know how to calculate what they represent, as shown in figures 1, 2, and 3 here. And what we can understand is how long has a system, or in this case, a mineral phase, been a quote unquote closed system, meaning parent decay, radioactive parents are decaying to their natural daughter products. And by measuring these ratios using this expression, the age equation, we can figure out the time since that system became closed. So what does this mean in this particular application? So the resulting data will yield the age that the mineral phase reached its closure temperature. So, well, what is that exactly? That's the idea that certain elements, especially in certain mineral phases like uranium, thorium, helium, during that decay process will not always retain, or at certain temperatures, that helium will diffuse out of the crystal system. And while initially this kind of seems like, you know, maybe this is a limitation of this methodology, it's actually quite useful because the temperature at which the retention, implantation, or ejection that occurs in various mineral phases and under various mineral shapes is very well or fairly well understood in many systems. One area, again, in one of the research questions that I call out is that the uranium, thorium, helium information in mineral phases, that data can be expanded on greatly. Currently, we do a lot of work in zircons and apatite. And so that's kind of what the state of research is at this point. But closure temperature effectively will show the time since that mineral was at a certain, or at that temperature. So what use does this have? Well, when we look at the suitable phases and its applications, we think about apatite and zircons, and these are two common accessory minerals that will contain tens to hundreds of parts per million of uranium and thorium, and they can hold on to the helium, the daughter product, for geologically meaningful lengths of time, as long as the temperature doesn't get too high. So when the temperature gets higher, this helium will diffuse rapidly out of the apatite or zircon minerals at temperatures greater than about 70 degrees Celsius. But what this means is that we can use uranium, thorium, helium in systems, say, close to the surface at low temperatures, to understand the erosional, uplift, incision, various processes that occur close to Earth's surface. And so what we can think about this and how we kind of bridge this methodology with Earth system science is that it allows for us to couple an understanding of both deep Earth processes and surface processes over extended timescales. And this is something that is traditionally not very easy to do, that coupling of both the deep Earth and the surface process, and looking at older, longer timescales, older applications. So some current applications of this is to look at unconformity development, long-term burial and erosional histories, and histories of topographic evolution, and specifically relating these to tectonics, mantle dynamics, erosion, and the climate. So some notable uranium, thorium, helium, and Earth system science connections. So Rayners et al. 2007 was one of the best papers that I found. And they basically displayed these key facts regarding the applicability of the method. And one was that the uranium, thorium, helium system does have environmental applications outside of uplift and incision. And they also found that apatite fractionates over the land surface. So this work mostly focused on wildfires and wildfire reheating or resetting of apatite grains. And they use this to kind of date and understand wildfires, in geologically old wildfires, and show that that the effects from these wildfires, when you're looking at how apatite is fractionated over the land surface, that this can tell us a lot about the erosional histories of landscapes on a fairly small scale, which is a novel contribution of this method. Another interesting connection was done by Flowers et al. In 2012, and this is fun because this is the only uranium, thorium, helium paper to ever make the New York Times front page. And this was done so because the apatite helium dates were combined with apatite uranium, thorium, helium ages, and they dated the formation of the Grand Canyon to nearly its modern depths at approximately 70 million years ago, which is a stark change to the conventional models that date the entire formation to only 5 to 6 million years ago. So this vast change in the conventional thought of the landscape evolution that's argued is using data that is technically self-consistent. The corresponding landscape evolution and change in timescales are also, again, something that we can fairly easily relate back to climate and climate systems of the region. So that's the end of my presentation. And if possible, I would love to take any questions. Thank you.